Ready then to continue. We have the honor and privilege to have here Professor Charles Kane, which is Christopher Brownie Distinguished Professor of Physics in University of Pennsylvania. Has been awarded several prizes, and I will read them. The Art Prize, Physics Frontiers Prize, Frontiers Knowledge Award, Breakthrough Prize in Fundamental Physics. These at least 4 prizes. And we are very happy to have him, and we're very happy that he accepted our invitation. And so, thank you for coming.
Okay, well, thank you. It's really a pleasure to come. Happy. Thank you for inviting me. I teach on Monday and Wednesday, and so I managed to come for today. So, so I'll be here. So this meeting is really nice. Bringing together physics, mathematics, experiment all together, because this field of physics has all of this interplay between these things, and so it's a really nice thing. One of the big ways in which there's been this interplay is in the context of topology, in particular topology in Hilbert space. So quantum states, and we heard about this in Nikolai's talk. Quantum states can be characterized by topological indices, and this gives a way of characterizing phases of matter that have the same symmetry. Okay, and the classic example of this is the quantized Hall effect, which so I see the fonts don't completely work. I don't think this will be a problem though. So in any case, there should be a Z here for integer topological invariant. So the quantum Hall effect is, as Nikolai said, the mother of all the topological phases, and there are many more versions of that kind of thing. And it's all about the topology of quantum states in Hilbert space. And and there's a very rich interplay between the topology, topological invariance and symmetry, which leads to all the kinds of developments that have happened over the last 20 years. In topological insulators, topological superconductors, and crystal symmetries play a role as well. Okay, and these same topological ideas, they apply to insulators that have a band gap. They also apply in metallic systems. One can characterize topologically Weil semimetals or with symmetry direct semimetals. So the topology in Hilbert space is a big thing. So that's not what I'm going to be talking about. So I want to talk about a completely different application of topology to electronic systems. Okay, and in some ways, it's a simpler application, and in some way, so I'm going to expose my, somehow I have this superpower of noticing curious features about non-interacting electrons that nobody had thought was interesting before. And so this is going to be another example of that. And so what I want to talk about, I had going backwards. I had this realization that the Fermi surface of an ordinary metal is a topological object. Okay, so the Fermi surface of copper has these little necks that go out and intersect the Brillouin zone. And so really the Fermi surface of copper is like a fancy donut with 4 holes in it. Okay, and so there's a topological number that characterizes every metal, okay, which is the, basically the genus of its Fermi surface. And so the question is, does that number show up in any kind of response or correlations? The way the Chern number shows up in a response function, which is the quantized Hall conductance. Okay, so is there anything like that? When we have topological numbers in physics, I have this deep conviction that there should be some physical manifestation of that. Okay, and so I've written a series of papers, finding some of these things, and I'd like to share those with you. And so I'm going to start off talking about quantized nonlinear correlations in a Fermi gas. Okay, so this is in a way the simplest thing. And a related thing is the structure. This topological index shows up in the structure of the quantum entanglement in a metal. And then I'll go on and talk about some quantized nonlinear response and also a potential experiment that one could do using Josephson junctions. Okay, so I want to start off to talk about the quantized nonlinear correlations. And before I do that, so how does one describe this topological number that characterizes a Fermi surface? And I think the appropriate way to do it is to characterize it in terms of a topological invariant called the Euler characteristic. Okay, and so what the Euler characteristic is it's a number, and there's a mathematical formulation of it. One can write it as the alternating sum of the Betty numbers, but rather than focusing on that, it's maybe simpler to just think about the specific cases in 1, 2, and 3 dimensions. In 1 dimension, the Euler characteristic is just the number of pieces of the one-dimensional Fermi C. Okay, so it's the number of one-dimensional subbands, if you will. Okay, in 2 dimensions, what the Euler characteristic is it is the difference between the number of electron-like Fermi surfaces and the number of hole-like Fermi surfaces. So, for instance, in this case, if I have this is an electron-like Fermi surface where the Fermi surface encloses, filled states on the inside, electrons. Whereas on this side, I have a Fermi surface which encloses holes. Okay, and so they have an opposite sign of the Euler characteristic. If you have an open Fermi surface, which is neither electron-like or hole-like, then the Euler characteristic is 0. Okay. In 3 dimensions, the Euler characteristic is just is related to the genus of each component of the Fermi C. Okay. And so, of course, this topological invariant, it's an invariant in that you can smoothly deform the Fermi surface and it doesn't change, so it's a topological invariant. But it does change at a transition which is called a Lifshitz transition, and the Lifshitz transition occurs whenever you have a critical point in the band structure. The energy is a function of k, either a minimum, a maximum, or a saddle point that crosses through the Fermi energy, signifying a change in the topology of the Fermi C. Now, one more point I want to make about this is that there's a distinction between talking about the topology of the Fermi C and the topology of the Fermi surface. Okay, so the Fermi C is the thing that's inside the Fermi surface. Okay, and they're related to each other. So, for instance, in 1 dimension, every Fermi C has 2 Fermi points. Right, every interval has 2 ends. Okay, and a similar thing happens in 3 dimensions. So maybe you know that the Euler characteristic in 3 dimensions is 2 times 1 minus g, 2 times 1 minus and that's what you get from the Gauss-Bonnet theorem. And so again, it's similarly related by a factor of 2. But there's a difference in even dimensions. In 2 dimensions, for example, every Fermi surface has the topology of a circle, okay, which is trivial. Okay, and so in a sense, in even dimensions, the topology of the Fermi C has a little bit more information in it than the topology of the Fermi surface. Okay, so this is the Euler characteristic. So the question is, how does this show up in some physical quantity? Okay, and so what I want to start off with talking about is quantized correlations of the charge density. And so let me first talk about it in 1 dimension, because there's something very simple that one can do. So what I have in mind is the equal time correlations of the charge density. So this is S of Q. So S of Q is the thing that you measure in X-ray scatter. Okay, so just the density correlation function. And so in a 1-dimensional Fermi gas, this is kind of a calculation you can almost do in your head. Okay, so you know how to do it. Rho of Q is C dagger C, right? And so you just are calculating this product of fermion operators. You use Wick's theorem to contract them. And so what it ends up being is a sum over sum over K of the points that are inside the Fermi C, but K plus Q is outside. Okay, so it's exactly evaluating the size of this interval in momentum space that has a length of q. Okay, so it's exactly quantized q divided by 2 pi. And so this is if you have one Fermi C, if your Euler characteristic is 1. If you have another subband, then you'll get another contribution from that subband. Okay, and so it's q over 2 pi precisely times this Euler characteristic. So this is kind of a simple-minded, kind of trivial thing. In one dimension, we have a quantized density correlation. The thing which is kind of remarkable is that this formula actually has a generalization to higher dimensions. Okay, and so let me tell you what that generalization is. In 2 dimensions, I'm not going to talk about the 2-point density correlation. I'm going to talk about the 3-point density correlation. So
Can I just ask you a quick question? Was that your line of reasoning? You found something in 1D which had this kind of quantized behavior, and then you asked if it would be?
Yeah, I mean, so the whole game I play is I know lots of things about one dimension, and I try to generalize everything I know in one dimension to higher dimensions.
That's what my guess was.
Yeah. So let me just tell you. So we have a 3-point correlation, which is a function. So it's going to be a function of 2 q's, right? Because the 3 q's have to add up to 0. So it's rho of q1, rho of q2, and then minus q1 minus q2. And what that is equal to is so in 2 dimensions, the cross product of 2 vectors is just a number. Right? So it's the absolute value of q1 cross q2 divided by 2 pi squared times this integer topological invariant. Okay. Same thing in 3 dimensions. In 3 dimensions, I'm going to consider a equal time 4-point correlation, which is a function of 3 q's, q1, q2, and q3, and that's given by the absolute value of the triple product, divided by 2 pi cubed times this integer. Okay, and so these are a little bit less trivial than this. And I have to say, I had a reason for looking at this 3-point correlation. The reason I did it is what I'm going to tell you about next, which is because I was interested in calculating the structure of the quantum entanglement. And I discovered this formula in a very roundabout way. Okay, and so the first paper where we had this formula, I did a completely horrible, very complicated calculation. Ultimately, we really discovered it kind of numerically. Okay, that this works, but with the benefit of hindsight, let me try to show you the simple reason why this is true. Okay, because I think I can sort of convey that. And basically, what it ends up being is basically kind of an application of this famous old formula of Euler's for polyhedron. Okay, so there's this. So there's a topological formula where if you have a polyhedron and you count the number of vertices, the number of edges, and the number of faces, then and you take the alternating sum of them, it's always equal to 2. And that 2 is the Euler characteristic of a polyhedron that has the topology of a sphere. Okay, so this density correlation is kind of a version of that. And so the way to think about that is to think about what you do if you actually calculated this 3-point density. Again, rho is C dagger C, so you're going to use Wick's theorem to evaluate correct contractions. And so without dealing with the details, you're going to have a product of three terms, which are either going to be the Fermi occupation or 1 minus the Fermi occupation. Okay, and they are going to involve k and then k plus q1, k plus q1 plus q2. The point is that each term in this sum on k is going to involve points which are on the corners of a parallelogram. Okay, k plus q1, k plus q2, k plus q1 plus q2. And so a way that you can organize the integral over the Brillouin zone is to think of it as a integral over 1 unit cell of the lattice that's generated by q1 and q2 times the sum over the lattice. Okay, so it's just like if I have a crystal and I want to integrate over space, I can do a sum over all the unit cells and then an integral over just one unit cell. Okay, so that's what I have here. And so if I think about so I'm going to do an integral over just one, and this should be a parallelogram, not a square. So I integrate over one parallelogram, and so then I have the sum over the lattice. And what the sum over the lattice is going to be, there's going to be some terms that have one Fermi occupation. When I multiply this out, there are going to be some terms that have two Fermi occupations and some terms that have three. And so what the term that has one Fermi occupation, what that is so what I've essentially done on this is I've triangulated the Fermi sea. And I have, and so this sum here is just going to be counting the number of points in this triangulation of the Fermi sea. The sum, the terms with two Fermi occupations, which come with a minus sign, are going to count the number of links, and the terms with three occupations are going to count the number of triangles. Okay? And so if you work this through, what this is precisely is it counts the number of points minus the number of links plus the number of triangles. That's just like Euler's formula. Okay? And so what this evaluates is it evaluates the Euler characteristic of this triangulated region here. Okay? And now the thing is that provided this mesh, provided Q1 and Q2 are sufficiently small, this triangulated approximation to the Fermi sea will have the same topology as the actual Fermi sea. Which means that when I do the integral over K, of course, when I do the integral over the Brillouin zone, this whole lattice is going to slide. Okay, and some points will come and go, but so the individual terms will change, but the sum, the alternating sum, is guaranteed to stay the same. Okay, so I can so this is just the Euler characteristic. I can factor it out of the integral, and when I evaluate the integral over the unit cell, that just gives me the volume of the parallelogram, which is Q1 cross Q2. Okay, so this is the origin, and it's clear that this argument, it's harder to draw a picture, but that this argument can apply in any dimension. Okay, in 3 dimensions, it'll be the number of points minus the number of links plus the number of triangles minus the number of tetrahedra. Okay, and so this this formula is exactly true.
So it's that's a quick question.
Yes.
It's intimately connected to your Fermi statistics, this like cross product coming out.
Fermi statistics. Well, I mean, so certainly this minus sign, right, which gives me this minus sign, that's Fermi statistics.
Plus also, yes.
Well, yeah, that's right. So it's essential that we're talking about fermions here. So I don't think you'd get the same thing with bosons. Yeah. Pardon?
I was just wondering if you thought about bosons at all. 1D, for example.
Yeah. So there, of course, you have to have interactions.
Yeah.
Okay. And the interaction is going to complicate that complicated story.
A related question: if you take composite factors at 1/2,
yeah.
Fail?
Well, so again, one has to talk about interactions in that case as well. Okay, and so there's an issue. Okay, is that what I have next? Yes, there's an issue. Yeah. Okay. Yes. Good question.
Maybe before interactions, what does your formula? What do your formulas mean when you have this order?
Good question. Yeah. So this this formula is really built on having translation invariance. So if I have disorder, that's out the door. Okay. So this is so in order to having a clean system is essential to this this discussion. Yeah.
Just wonder how does the shape of the Brillouin play a role here?
No, it doesn't. No, the shape doesn't. It doesn't matter.
How do you visualize the Euler characteristics for geometrical shape that somehow holds to itself?
Well, right. You mean like copper? You mean like copper? Yeah. So yeah. I mean, given the fact that it's defined on a system with periodic boundary conditions, that doesn't prevent you from defining the Euler characteristic. So this surface has 4 handles on it. Okay, and so in a sense, it's kind of the same as this. Though you're right, there's a sense in which it's different too, in the sense that it's wrapping around. It has non-trivial cycles. The Brillouin zone has non-trivial cycles, but that doesn't interfere with the definition of the Euler characteristic. Okay, so I said there's an issue with interactions, and so again, let's go back to the thing I know lots about, which is one dimension, which is now in one dimension, of course, for non-interacting fermions, this is true, and in fact, it's also true that the higher point correlations are actually equal to 0 for free fermions. Okay. Now this reminds us of what happens in an interacting one-dimensional electron gas. Okay, because an interacting one-dimensional electron gas is a Luttinger liquid. Okay, and Luttinger liquids are easy, and in particular, the density correlations in a Luttinger liquid are easy to think about. And what we know is that they depend on the Luttinger parameter. Okay, so of course for non-interacting electrons, k is equal to 1, and we reproduce our quantized answer. But the interactions modify the quantization. Okay, so it's no longer integer quantized in the presence of interactions. Actually, it's still true that the higher point correlations are 0, at least if you have a Luttinger liquid, which when you bosonize it, is non-interacting bosons. Okay, so this is just a reflection of essentially Wick's theorem for the bosons. Okay, though of course the non-interacting bosons for a Luttinger liquid, that only applies to the Luttinger model of fermions, which has a perfectly linear dispersion. Okay, so even if you have non-interacting fermions and you have a dispersion that has curvature, when you bosonize it, the bosons will be interacting. Okay, and so actually these are kind of different things. Okay, the non-interacting boson problem is not the same as the non-interacting fermion problem. And this topological characterization I have right now, it applies to the non-interacting fermion problem. Okay, and in particular, so in higher dimensions, we have a similar kind of thing. So I showed you that we have this quantized 3-point correlation in 2 dimensions. The higher point correlations for non-interacting electrons we can show are equal to 0. Okay, but if you have interactions, the interactions will mess with the quantization. And so in fact, what we can show is that in a 2-dimensional Fermi liquid, the Fermi liquid parameters modify, the Landau parameters modify the quantization. So the bottom line is that this quantized density correlations are specific to non-interacting fermions. Okay. Now that said, there's a related phenomena. In fact, which was the reason I went down this road to begin with, which is that these density correlations are related to a quantized structure in the quantum entanglement. Okay, and what I'm going to show you is that the quantized entanglement in say a 3-dimensional Fermi liquid, they remain quantized even with interactions. Okay, and so stay tuned for this. But even if you have non-interacting fermions, you might ask, one can have pretty weakly interacting fermions, and so is this something that one could measure? And so let's think about how you might go about trying to measure this. And so one idea that we had was, the AMO people can make Fermi gases of atoms, okay, fermionic atoms, and and it's a straightforward thing for them to measure the density correlations. Okay, and so in this in a atomic gas microscope, then what they can do is they can have atoms in a trap, and essentially what they do is take a picture of the atom gas where they see where all the atoms are. Okay, and so this has all of the information about the correlations in the density. So in particular, one can extract the 3-point density correlation from this. Okay, and so what we propose that they do is to actually measure this 3-point density correlation. And just as a matter of feasibility, what we did is we did a calculation on a finite system, okay, that would have about 100 fermions in it, okay. So it was a 14 by 14 grid. We did a tight binding model, and it's a straightforward thing to compute this correlation function, compute what they would measure. And so what this is a plot of is it's a plot of this this 3-point correlation function as a function of R3 fixing, R1 and R2 are fixed here, and then it's as a function of R3. And so there's some correlation which you can sort of see in real space. But if you Fourier transform it, then it has a structure this linear structure which sort of tells you about this Q1 cross Q2 behavior. Okay, and it looks like it should be possible to extract this experimentally. Okay, and so this is we're hoping that the experimentalists will jump on this. Yes.
What about in the solid state context? Do you have a proposal there?
Yeah, I do. In principle. Okay, I'll get to that next. So so very good question. So in a solid state context, what could you do? So the way you measure S of Q is you do X-ray scattering. Okay, so can you do something like that? Okay, and so, but we need something a little bit more than S of Q because we need the 3-point correlations. Okay, and so our idea, so what you do to measure S of Q, so first of all, we want the equal time correlations. So our idea is to sort of take a snapshot, okay, with maybe a pulsed X-ray, okay, and then if you measure the number of scattered photons in some direction, then that is how you measure S of Q, okay. And so in order to measure the higher point correlations, what we would need to do is to measure correlations between these scattered intensities. Okay, so what's going to happen is if you look on the screen, there's going to be like a speckle pattern. Okay, and there are going to be correlations between different scattering directions. Okay, and so there are 2-point correlations of the intensity, and they will tell you about the speckle pattern essentially. The universal term is going to be in the 3-point correlation. Okay, and so we have a prediction for what the correlation between these would be. Okay, now I think this is a tall order for experimentalists, but I don't think it's completely out of bounds. Okay, and so this is our best guess for how to measure these topological correlations in a solid state system. Okay, so so I told you that again one would have to have in order to have this quantization, one would have to have a weakly interacting Fermi gas, which maybe is not too much to ask for. And in principle, one could understand the corrections to this due to the Fermi liquid parameters. Okay. But I told you that there really is something which is more robust than that, and this has to do with the structure of the quantum entanglement in a Fermi gas. And this was my original motivation for actually looking into the density correlations. And so the connection between topology and entanglement has a long history. And going back to the topological entanglement entropy, which is a way of characterizing strongly interacting topologically ordered states in 2 dimensions, where, and this goes back to Kitaev and Preskel and also Levin and Wen, where what they propose to do is to think about the entanglement between 3 regions and define a kind of mutual information between these 3 regions. So this sort of combination of the bipartite entanglement entropies is designed so that all of the area law pieces sort of subtract off, and you get something which tells you about the intrinsic correlations between 3 regions. Okay, and so for the topological entanglement entropy, this mutual information was related to the total quantum dimension, which is a topological number that characterizes the structure of a strongly interacting topological phase. Okay. Now there's a different version of entanglement that applies in a one-dimensional system, and so this is another one-dimensional thing that I knew about that I wanted to generalize. And so there's a famous old result in conformal field theory due to Carty, which says that if you have a one-dimensional system and you cut it in half, you can consider the bipartite entanglement between 2 regions. And in a conformal field theory, there's a logarithmic divergence in the entanglement entropy. And the coefficient of that log tells you something topological about the conformal field theory. In particular, it tells you the number C, which is called the chiral central charge. Okay, and now a one-dimensional Fermi gas is a simple version of a conformal field theory, and in that case, the C is just equal to the number of Fermi points you have, and that's exactly this Euler characteristic. Okay, and so so in fact, the bipartite entanglement entropy probes this topological number that I have in 1 dimension for a one-dimensional Fermi gas. Okay, but one thing that is interesting about this is that in a Luttinger liquid with interactions, C doesn't change. Okay, C remains equal to 1 even when the Luttinger parameter K is not equal to 1. Okay, and so we have some reason to believe that this is more robust. But if you calculate the, for a free Fermi gas, if you calculate the bipartite entanglement entropy, so there's a way you can calculate the entanglement entropy, and what that calculation ends up being is it's very closely related to the density correlations. Okay, and so whereas the density correlations are modified by the interactions, somehow that modification goes away when you calculate the entanglement. Okay, and so that was my motivation for thinking about a higher dimensional version of this, because I know in 1 dimension C is insensitive to the interactions. Okay.
Question.
Yeah.
So is there an assumption of linearized spectrum here? So it's like kind of a low energy 1D.
It's low energy, yeah. It's low energy, but the thing is everything is the nonlinear corrections are irrelevant, so they don't affect the log. They don't affect the coefficient of the log. Yeah. Yeah.
Also, principal C changes by half integer.
For Majorana,
C could be a half.
well, C could be all kinds of numbers in conformal field theories, right? What?
Not continuous.
No. I mean, you can have. I mean, if you
Rational could be rational.
Rational, yeah. C is usually rational.
You can't have any C can't any number.
No. But C doesn't have to be an integer in a topological phase. I mean, we know lots of examples where C is.
In those cases, then there's no identification for chi-f. It's chi-f integer.
No, that's right. No. I mean, chi-f is we're talking about non-interacting electrons. Okay. Yeah. So though maybe you could say that if you have a Fermi gas, even if it's interacting, then chi-f turns into C, which is an integer.
It seems like almost what you're trying to suggest.
Yeah. No. So in the cases I'm talking about, C is going to be an integer. Okay. But it is interesting that that there's sort of a fractional version of C, right? And that the integer quantum Hall effect, it's always an integer, right? But there's a fractional quantum Hall effect. So right now I'm just talking about the integer quantum Hall effect. Okay. So okay. So this motivated me to think about generalizing this to higher dimensions. Now, the most naive thing to do would be to think about the bipartite entanglement. So I have a two-dimensional system, and I cut it in half and ask what the entanglement is. And this is actually a well-known, people have looked into this long ago. And basically what you get is you basically get an area log entanglement that has a log divergence to it. Okay, and that sort of makes sense because you know that if you cut a system in half, you're going to get an entanglement that scales with the size of the boundary. Okay, and in 2 or higher dimensions, the size of the boundary has units, and so the coefficient of that is going to be a non-universal number. Okay, so it's not going to be quantized in any sense. So the problem, but in 1 dimension, of course, 2 regions meet at a point. And a point doesn't have any dimension, so the coefficient of that is going to be universal. So what you need is things that are associated with a point. And so in 2 dimensions, 3 regions meet at a point. And in 3 dimensions, 4 regions meet at a point. It's kind of hard to parse this picture. It's sort of like a 3-dimensional version of a peace sign. Okay? So that motivates us to consider the mutual, the multi-party entanglement between different regions. Okay, in particular for a 3-dimensional Fermi gas. So I'm going to skip 2 dimensions. There's a reason for that. I'm going to skip to 3 dimensions and talk about the 4-party mutual information between 4 regions. And so this is something that we can compute. Okay, and so again, it's the it's some combination of the bipartite entanglements, and the bipartite entanglements we can compute. It ends up being a calculation involving calculating the density, the correlations in the charges in those 4 regions, which is an integral of the density correlations. And what we were able to show in doing this is that for a free Fermi gas, there is, in fact, a universal logarithmic divergence in this mutual information. It's actually log cubed, and the coefficient of the log cubed is precisely the Euler characteristic of the 3-dimensional Fermi. Okay? So this is, in a sense, it's a kind of a generalization of the Cardy-Calabrese formula in a 1-dimensional CFT. Yes? Lower order, you mean lower order in log? Yes, that's right. There will be. I mean, obviously there will be because the number inside the log is non-universal, right? So there will be non-universal log squared and log terms. It's the term which is universal is the log cubed term. Yes. Okay. All right. So one other thing that we can do, so the way we do this calculation is, so to calculate the entanglement entropy, you use a replica trick, okay? And then when you do the replica trick, you're basically end up calculating a density correlation function, okay? And now the thing is that we can do this replica trick calculation in 1 dimension, okay? Where we calculate the density correlation. And in 1 dimension, the density correlation is modified by the Lutnier parameter. Okay? But in the end of the day, we know that the entanglement is not modified because the entanglement measures C. Okay, and so by going through that calculation, you can understand why it is that the interaction corrections drop out in the entanglement. Okay. And it has to do, I mean, basically the interaction corrections amount to including sort of RPA corrections in the, you're summing RPA bubbles basically. And those RPA bubbles drop out in the replica calculation. Okay, and so the same thing happens in 3 dimensions. So we can include interactions perturbatively, and we can understand that for the entanglement, they do not change the answer. Okay, so we believe that this mutual information is not perturbed by interactions, at least if the interactions are weak. similar to C in one dimension, and so that this topological invariant really characterizes distinct topological Fermi liquid phases. Okay, so there's more to it than just free fermions. Okay, yeah. How might? Oh yes.
Just out of curiosity, if you take the just the entropy.
What's that?
Take the entropy like SA.
Yes.
So of course you have the first term, which is like L square log L.
Yes.
But do you have other correction and then that term? Like
yeah,
the way
yeah.
you extract
So right. So you could ask if I just look at the bipartite entanglement of a region.
Yeah.
So what is it? So where the singularity comes from is it comes from having a corner.
So it's a corner contribution.
Yes, it's a corner contribution. Because the thing is that in order to have these regions meeting at a point, there has to be a corner. They have to meet at corners.
If I remember correctly, in 2 dimensions, you actually the way you cut the Levin-Wen or Fresco, you remove the corner contribution to solely focus on the topological correction.
No, I think the
subleading correction, which is constant.
Yeah, I think the way you cut, in this, remove the corner.
doing the Kitaev and Preskel did it a different way than Levin and Wen.
Yeah.
This is the Kitaev and Preskel way, which sort of the corner is there. But the thing, what I'm saying is that it is the corner term that survives in this mutual information. Okay, and so I think that's where if you wanted to look for something in just the bipartite entanglement entropy, then where it's going to be is it's going to be in the corner contributions. Yeah. Okay. How am I doing for time? So I don't want to.
About 17 minutes.
Oh, I have some time. Okay, so it's 12 o'clock. I want to finish.
Exactly.
Okay, good. Okay, so so I want to tell you one more. So we have some quantized correlations for non-interacting electrons. We have some quantized entanglement. The problem with entanglement, I don't know how to measure entanglement. Okay, and and what we have in the quantum Hall effect is we have a quantized response function that you can measure, a quantized conductance. So is there anything like that? Okay, and so again, I'm going to play my game of, I know lots of things about one dimension. And another thing that I know about one dimension is if I have a ballistic one-dimensional electron gas, then there's a quantized conductance. It's kind of like the quantum Hall effect, right? If there's no scattering. So, and this is the Landauer formula, okay? So in a ballistic one-dimensional electron gas, there's a quantized conductance, which is, n e squared over h. So what's n? N is just the number of one-dimensional subbands that you have. So it's exactly my Euler characteristic. Okay, so the question is there some kind of generalization of this? Okay, and this is actually the first thing the first generalization I tried to come up with. And so in order to motivate this, it's useful to sort of kind of think about why the Landauer formula is quantized, okay? Because it's kind of related to the quantum Hall effect, okay? So what you can imagine is if you have a circle in one dimension, and so the quantization of the quantized Hall effect you can understand using Laughlin's famous flux threading argument. Okay, and so let's imagine that we have a circle and we adiabatically thread a flux through the circle. Then what's going to happen? So you know what happens. There's when you thread the flux, there's a dB dt, and so then there's from Faraday's law, there's an electric field which accelerates the electrons going around. And at the end of the day, what happens is when you thread the flux, every electron moves over in K. So when you thread one flux quantum, every electron moves over in K by one space. Okay? So that at the end of the day, what you have done is you created one extra right-moving electron and removed one left-moving electron. So you've transferred one electron from one side of the Fermi sea to the other side of the Fermi sea. So that's what happens when you thread a flux. Okay, and so I can so if I count the number of right-moving electrons, then when I do this flux threading, thought experiment, then that changes by precisely this topological number chi f. Okay, of course, this happens in every one-dimensional subband. Okay, so how might we generalize this to 2 dimensions? Okay, and so in 2 dimensions we have 2 fluxes. So now let me imagine that I wrap my 2-dimensional Fermi gas onto the surface of a donut, onto a torus. Okay, so it has 2 fluxes, and so what I want to consider now is I want to consider the number of electrons that are basically moving up and to the right. I want to ask how that changes as a function of the fluxes. Okay, and now of course if I thread a flux in the x direction, then what's going to happen is that every state is going to move over by one space in the x direction. Okay, and so I'm going to have extra electrons everywhere on this side of the Fermi sea. Okay, just like what happened up here. Okay, so there are lots of extra electrons, moving up and to the right. Okay, but the thing is, then I can ask, well, of those, how do they change if I thread the flux in the y direction? Okay, and now for all the electrons out here, they don't care whether I thread the flux in the y direction. They're still always going to be going up and to the right. It's only the one that's down here that's going to change its mind. Okay, so in fact, if I calculate the change due to both the x and the y directions, then what it does is you just get one contribution from this point here. And in fact, I want to argue that this is the Euler characteristic. So if you have a more complicated looking Fermi sea, then there are going to be contributions from every point on the Fermi surface where the velocity is basically in the x direction. And there are 2 kinds of points. There are points which have a concave curvature, and there's points that have a convex curvature, and the contribution is going to have an opposite sign at those 2. And if you take the difference between the number of concave points and convex points, it's not too hard to convince yourself that that is in fact precisely the Euler characteristic of the Fermi sea. Okay, and so for example, in this example, there's one electron-like Fermi surface on the outside, and there are 2 hole-like Fermi surfaces. So the difference is -1. Okay, and if you do the count, you have +1, -1, +1, -1, -1. That's also -1. Okay, and so this precisely measures the Euler characteristic of the 2-dimensional Fermi sea. Okay, so now one can ask, so this is sort of a Laughlin-esque thought experiment. How could we do a real experiment? So what you need is, instead of threading fluxes on a cylinder, you want to apply voltages. Just like in the Landauer formula, you apply voltage between 2 reservoirs. So a version of this would be, you need to have maybe a 2-dimensional electron gas, and then you can apply voltages either in the x direction or in the y direction. And so one thing you can do is you sort of do a pulse in the x direction and a pulse in the y direction, and you want to figure out what's the change in the charge here that's due to both pulses. So you do the pulse in the x direction and the y direction, and you figure out that you evaluate this difference basically. And so the prediction then is that should be sort of quantized with this Euler characteristic. Now, so one way of doing it is by doing these sort of pulses. You could also imagine a frequency domain experiment where you have AC voltages, then you wouldn't have to do the subtraction because you measure the current at the some frequency. Okay, and so the prediction is that there's a universal term that has this this sort of frequency dependence. Now there's some caveats to this, which is, so this calculation is an exact calculation for a infinite two-dimensional electron gas with no scattering or interactions. Okay, so that's the setup where one can derive this formula rigorously. Okay, now that's not what you really have in a real experiment. You don't have an infinite system. So in particular, if you have a finite system, then that's going to set a lower bound on how low the frequency can be. Okay, one way of thinking about this, if you do this pulse thing, you know, if I do the first pulse on Monday and then I do the second pulse on Tuesday, you know, everything will have gone off into the leads and equilibrated before I did the second pulse. So the first pulse would be completely forgotten. Okay, so you need to have a big enough system that the first pulse has not been forgotten when you do the second pulse, and that in turn puts a lower bound on the frequency that you can operate at. So it's not so simple to think about how to get this into an experimentally accessible regime. Another caveat is that, you know, again, this calculation was for free fermions. One can put interactions into this, and the interactions do change the answer, just in the same way that they did for the density correlations. Okay, so this would apply to a non-interacting Fermi gas. So one could one can ask the question, can one do better than this? Another version of this. So notice that it has this, you know, this frequency dependence. So one of the frequencies comes because if I calculate the current, which is dq dt, then I'll get rid of one of these frequencies. But I have a response to Vy divided by omega. And so what's Vy divided by omega? Well, you know, that's like the phase of a superconductor. You know, so the velocity is like the derivative of the phase in a superconductor. And so what this suggests is that maybe one could replace, say, the Y voltage by a phase difference in a superconductor. Okay, so that motivates us to think about a Josephson junction type of setup. Okay, and so that's going to be the last thing that I talk about. And so what I want to imagine is it's sort of like a point contact. Okay, you know, usually at a point contact, what you do is you pinch off a two-dimensional electron gas with insulating, you know, gates that deplete the two-dimensional electron gas, and you pinch it off with sort of an insulating barrier. Okay, here what I want to do is I want to pinch it off with a superconductor, with a superconducting gap. Okay, and but the thing is if the phase difference across the superconductor is pi, then there will be Andreev modes that are zero energy Andreev modes that propagate along the junction between the superconductors. Okay, and so this is a classic superconduction problem. You know, imagine you have an infinitely long channel like this, and you have a pi junction. Okay, so then it's like you have a domain wall in the superconducting order parameter, and then there's going to be a topological zero mode that gets bound to the domain wall for every value of k that is inside the Fermi surface. Okay, so every value of k inside the Fermi surface, there's going to be a pair of Andreev zero modes. Okay, now, but the thing is if you're outside the Fermi sea, if k is outside the Fermi sea, then you don't have these zero modes. So what happens to the zero modes? What has to happen is that when they get to kf, they have to sort of go up and go down. Okay, and so when they go up and go down, they have a finite velocity. They have a slope. They have a finite group velocity. So those states can then carry transport. Okay, and so our idea is to measure the transport in these dispersing low energy Andreev modes. Okay, and so what we can show is that so we have these these modes, they disperse at kf, and so the question then you can ask is, if you're a quasi-particle in one of these low energy Andreev modes, then you're propagating, you're moving, you're propagating along the junction. Eventually, you're going to get to the lead. You're going to get to sort of a two-dimensional electron gas that's not superconducting. Okay, and so what happens? What do you turn into? Okay, and so basically, the electron-like ones are going to turn into electrons, and the hole-like ones are going to turn into holes. Okay, and so basically, you can determine whether an electron whether this will turn into an electron or turn into a hole, and that determines the sign of the current that it carries. Okay, and at the end of the day, what we can show is that if you have just a simple electron-like Fermi surface, then what you get is a function. So what I want to do is I want to do a three-terminal measurement where I have a source and a drain which is grounded to the superconductor. Okay, so the drain and the source are at 0 voltage. I apply a voltage to the source, and then I want to measure the current in the drain. Okay, and so what we can show is that if the source voltage is positive, you get a quantized sort of Landauer conductance. If the source voltage is negative, you actually do not get there's no current. Okay, and so this is actually kind of an unusual current voltage relation. It's like a rectifier. Okay, and you see the thing is that whether you get the current at positive voltage or negative voltage depends on whether you have an electron-like or hole-like Fermi seam. Okay, and so that gives some indication that this is probing the topology. And so if you have both electron-like and hole-like components to your Fermi seam, then what we can show is that at positive voltage, you're basically counting the sort of the red points. Okay, and at negative voltage, you're counting the blue points, basically. The difference between those numbers is precisely is this Euler characteristic. Okay, and so at the end, so if you were to so we have a different slope at positive and negative voltage. If you apply an AC voltage, then it's going to act like a rectifier. You apply an AC voltage, that's going to generate a DC current. And the DC current is going to depend on the difference of these two slopes, which is precisely quantized by the Euler characteristic. Okay, and so that's so this would be something that would be kind of nice to measure. I mean, even measuring something like this, I think, would be an interesting thing to measure the transport in these propagating Andreev modes. Okay, because this is not the usual way one configures Josephson junctions. Okay, so usually you're interested in the current flowing in the superconductor. Okay, here I want to think about the current flowing in the channel perpendicular to the superconductor. Okay, so this is a little bit different geometry than one usually does for a Josephson junction. And so I'm out of time. We have some ideas for how for places one could look in this. In bilayer graphene, one can have some control over what the Fermi surface looks like, and so it may be possible to sort of get into different regimes. We've done some calculations on these, but since we're all hungry for lunch, let's finish up, and I'll just conclude. So the Fermi C is a topological topological object, and this shows up in some potentially interesting things. So thank you very much.